I will see here, make sure I got this. Every so often I forget to plug in the mic cord. There we go. I will start. All right. Dear Heavenly Father, we thank you for this day again. I thank you for this class, this week. It's about to start. We thank you for the weekend to relax and refresh. And just pray that you guide our steps today. Help us to glorify you and what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so here's an example. Let's try example 1. Let's suppose A is equal to, I don't know. Let's try this one. 1, 0, 1, 0, 1, 0, 0, 0, I don't know, 2. Let's see if we can calculate the inverse of this matrix. All right? So, find A inverse, solve AX equal to ABC. So we'll do these things. All right, there's the problem. So the algorithm, the fastest way to calculate this, well, the fastest way is to guess. If you've got technology, you could just plug it into MATLAB or such and do it that way. But of course, we don't have MATLAB on the test, so that's kind of a problem. And also, we'd like to understand how to do these things by hand, because you might face a symbolic problem where you need to do it by hand. And anyway, so all right, so what's up? Well, this is a really easy problem, isn't it? So I just do what? Row 3 minus 2 row 1, I think. What's that give me? Oh, my bad. I want to do the other way around, right? No. Hold on a second. That's not what I want to do. What do I want to do here? 1/2 row 3. How about this? I think what I want to do is I want to do row 1. You could do 1/2 row 3. That's a good move. Sure. But I'm going to do row 1 minus 1/2 row 3. That's what I want to do. Sorry, guys. I'll get with eventually here. Let me. So the modified row is the one I'll write in red here in just a second. So we're modifying row 1 minus 1/2 row 3. So the start with nothing changes. I got 1, I got 0. But if I take 1 minus 1/2 of 1, I get 0. And over here, still the 1, still the 0, but now minus 1/2 for the upper spot there. Okay? So what I'm doing here is I'm clearing out above the third pivot, right? I mean, it was already, basically this matrix was pretty nice. It already had columns 1 and 2 worked out, so we just had to worry about column 3 basically. Now, let me do what you told me, which is to do row 3 over 2, right? So that's just going to change the third row here. Yeah. And we're still going to have our 1, 0, 0, 1, 0, minus 1/2, 0, 1, 0, 0, 1, 0, right? So by the theorem we worked out last time, what does this mean? If we do row reduction on the identity matrix put next to A, right? And we can do row reduction until we put the identity, basically we start with the identity matrix here, right? And we end with it here, right? If that's possible, then the theorem says that whatever's over here has to be what? This is the inverse of A, right? So, and of course we can check that right? If you multiply that matrix times the given matrix, you get, the right thing from the first two columns. In the third column, notice what happens. Minus 1/2 plus 1/2 gives you 0. When you multiply that third column by the first row, you get 0 for that third column times the second row. And then finally you get, a 1. You easily check. It's easy to check. You can check that A times A inverse indeed is equal to the identity like we like. All right? Okay, so now that we have A inverse, if we want to solve AX equals to ABC, what do? Well, that says that A inverse AX is equal to A inverse times ABC. But A inverse times X is just IX, right, which is just X, is equal to, apparently, 1, 0, minus 1/2, 0, 1, 0, 0, 0, 1/2. I multiply that by my ABC vector, and here you go. That gives us A minus C over 2, B, and C over 2, right? What this means, among other things, is that if I was to calculate the reduced or echelon form of like A with ABC here, what would happen? This is just a side comment. By the way, if we were to do this would give us what? We get a identity, right, for the first columns of A. And then what would happen is this ABC would reduce to what? A minus C over 2, B, and C over 2, actually. That's what would happen there. Any questions before I go on? Yeah.
What was that, by the way?
Oh, by the way, just a side comment. Yeah. See, if we solve the system AX equal to this, the solution is that. Which means that if we were to row reduce the augmented coefficient matrix here, it would work out like that. Yeah.
Is one generally quicker than the other, or does it depend on which one?
Is it quicker? I think it's almost always, well, I mean, it depends on the context, I suppose, but for a symbolic problem, I tend towards find the inverse and multiply. If it's a numerical problem, like if I just had ABC was like 10, 7, 0, it's probably, it's almost certainly quicker just to put the augmented coefficient matrix down and do the row reduction to find the solution. Yeah. And also, the other thing to think about is solution by inverse is not general. Why? It's because it doesn't solve all problems. If I have 3 equations and 3 unknowns, I can only solve by multiplication by inverse if the inverse exists, right? But there's plenty of problems where the inverse doesn't exist, right? All you need is some linear dependence amongst the columns, and then you can't multiply by inverse, but you can still do row reduction. So row reduction is a general method. It will reveal whether or not there's a solution. All right, so that was just another example to try to bring more depth to what we did last time. So I'm going to move on here. Now, if you look at the course planner, I mentioned something about factorization and Chapter 9. I'm putting that off till Wednesday. My goal today is to talk about everything besides that. So one of the next things we need to talk about is so-called block multiplication. So block multiplication is an interesting idea. So here's the deal. If A and B have, let's just say, suitable partitions with matching blocks. So blocks is just another word you might say for like a submatrix, okay? so submatrices, then we may multiply A and B by treating blocks as if they are numbers. So I think so I have a more, verbose and perhaps more technically correct definition in the notes. I'll let you look at that. But for the sake of us understanding each other, let's just look at an example. Although this example is still kind of an example of examples, but here we go. A11, A12, A22, A2, my bad, A12, A22, A13. Oh, just a second, guys. This is the problem with me teaching at 8:15. What do? I make dumb mistakes. So A11, A12, what goes here? 2-1, thank you. 2-2, 3-1 maybe would be better, yeah? There we go. Okay, now we've got them properly numbered. And suppose I've got another matrix over here, which has got like B11, B12, B21, B22. See, the thing here is if I asked you to multiply these two matrices, right? I hope you'd know how to do it, right? What would we do? I mean, this appears to be a 3 by 2 times a 2 by 2, right? So you just do what? You do like A11, B11 plus A12, B21, and then let's see here, I get A11, B12 plus A12, B22. And let's see here, the next one gives me like an A21, B11 plus A12, my bad, A22, B21. And then over here we've got a A21, B12 plus A22. If I can stop. And there's one more, right? What goes in the third row here? A31, B11 plus A32, B21, and then A31, B12 plus finally A32, B22. At this point, you might be like, okay, this would have been helpful like a week ago, This is just how matrices multiply, right? But let me tell you what I'm saying here. I'm saying that the A11, the A12, the B11, the B12, all of these things I have on the board, they themselves can be matrices. So provided that these products make sense, right? I'd have to have, for instance, if A11 was like M1 by, say, M1 by N1, for instance, suppose this is that block, right? Then this down here is going to be like M1 by N1, right? So in order for this to make sense, what does the size of the block on B2 have to be? In order to make this multiplication over here, we need a what? We need a N1 by whatever, right? By P1, let's say. Right. And if you start thinking about this, then if this has M1 rows and N1 columns, these all have what? N1 columns. So basically, you have to have the size of the blocks matching up, all right? But if the size of the blocks match up, then you can multiply them as if they were numbers. All right? So rather than dragging you into a litany of exactly the numbers, like the matching size and like coming up with letters for the matching size blocks, let's actually work an example which is like more specific here. So example 3. So let A, B, C, and D be square matrices of same size. All right. Actually, there's no D. Let's just do ABC. ABC, square matrices. We'll make this D a 0, okay? Square matrices of the same size, and we'll form M as follows: A, B, 0, C, all right? And then the question I ask is, what conditions should we insist on for M to be invertible? So, like, just for the sake of discussion, we're supposing that, this matrix M, well, let's say that the matrices A, B, C, and D, A, B, and C, like, those are, like, let's say they're K by K blocks, right? How big would that make M? How big would M be if these matrices are K by K? What are we talking about? M is a what? It's like a 2K by 2K matrix, right? Because each one of those blocks is K by K. So you put it all together. For example, if A, B, and C were 2 by 2s, this would be a 4 by 4 matrix. All right. This is actually an example of what's called a block. Well, it's not block diagonal. It's upper block diagonal, I guess. If B was 0, this would be a block diagonal matrix. All right. Okay, so we're looking for, let me propose that what we're really trying to find are X, Y, Z, and W, perhaps, right? We can look at it this way. We're trying to find X, Y, Z, and W, right? Such that what? M inverse is equal to what? The identity matrix, right? So here, that means we're up against A, B, 0, C, times these matrices we don't yet know, X, Y, Z, W. And I just want to work out if we can figure out some nice conditions that will make the given matrix invertible. All right? Now, it turns out after test 1, we're going to learn something called the determinant, which will give an easy answer to this. We'll just say, well, the determinant of M needs to be non-zero. And it turns out that for a matrix like this, there's an easy way to calculate the determinant. But we don't know that yet, so we're kind of stuck with what we're doing. And that's fine. Right? But the identity matrix here, yeah.
Are we allowed to use the determinant?
You are not allowed to use the determinant on the first test. Thank you. Good question. So 2K, no. The determinant is not on the list of allowed steps for test 1. Yeah, sorry. But otherwise, it makes some questions I can ask which are interesting uninteresting. And, it forces me, if I don't take the determinant off the table for test 1, it's going to force me to ask some more complicated questions than you want me to ask. Simply to ham-handedly disallow the use of the determinant. You don't want that. Okay, so anyway. So this is the 2K by 2K identity matrix. Of course, we can write that as the identity matrix and the identity matrix like this. All right, but block multiplication, how does that work? Well, we just multiply. So we have A times X plus B times Z. And over here we have A times Y plus B times W. Now I said it's just like multiplying numbers. That's partly true, but it's partly false. The way it's false is that the order of the letters absolutely matters. Like I can't just rewrite this as XA, right? Matrix multiplication does not commute, so it has to be AX. It has to be AY. I can't just carelessly write XA. That wouldn't make sense here. Matrix multiplication doesn't generally commute. Now, why is there only two? There's one term down here. Why is that? Because of that 0, right? The 0 made that go away. All right, so we've got I, 0, 0I. And if you don't mind, I'm going to drop the sub k on the identity matrix since I think it's clear enough from what we're doing that those have to be k by k. Now, all right. So this is actually 4 matrix equations, right? In order for these two matrices to be equal, I need what to go on here? So I need AX plus BZ is equal to the identity. I need AY plus BW equal to 0. I need CZ to be equal to 0. And I need CW to be equal to I. So here's a question. If we look at this last equation, CW equals to I, what does that tell us about C? And also about W, technically. What does that mean? Yeah.
They're both non-zero.
They're both non-zero. I think that's true. Yep.
One of them is the inverse of the other.
One of them's inverse of the other. Correct. Because remember we have, so context, these are both square matrices. Their product is the identity. So by the theory we looked at the other day, that forces these to be invertible matrices. And indeed, they have to be the inverses of one another. So if we're going to solve this equation, this implies that C inverse exists. So C has to be an invertible matrix. And what? We know what to do for W. W has to be equal to C inverse. Great. W has to be equal to C inverse. But what does that tell me then? Let me number these things. 1, 2, 3. So we've used 4. What does 3 tell me now?
Zero.
Yeah, 3 tells me that C inverse CZ is equal to C inverse times 0, which is to say what? Just what you told me, that Z, I times Z, which is just Z, is equal to 0. All right, well that's 50% done. We're 50% done finding the inverse to M. 2 more blocks to go, right? So we used 4, we used 3. We just found out Z was 0, right? So if we look at 1, that gives me what? AX equals to? Apparently I, right? So what did we learn about X? Aha, well apparently X is also equal to A inverse, right? So by the way, we need A inverse must exist, right? Because, I mean, we're trying to discover here together, in order for this block matrix to have an inverse, what do we need to know about the blocks? Well, apparently, if it's going to have an inverse, we need that the A block and the C block, those both must be invertible by this algebra, right? And now we have to use, what equation do we have left to use? We still got 2 to use, right? What's that gonna do for us here? Well, we already know that, let's see here. What blocks do we've got? We've got, what do we figure out? Our m, I'm going to keep score up here. We got mn versus what so far? The x was what? A inverse? Yeah. And down here we had a c inverse, right? Z was 0. So we're just trying to figure out, our goal is to find what now? Yeah, we're trying to solve, we need to solve for y. That's all that's missing. That's the only missing puzzle piece here. So I have ay is equal to minus bw, right? But that tells me that y is equal to minus a inverse times bw, right? But what was w? C inverse. So y is equal to minus a inverse b c inverse. And so there you go. That's the missing puzzle piece. Minus a inverse b c inverse. And there you have it. That's the inverse for this block matrix, provided that A inverse and C inverse exist. If either A inverse or C inverse fails to exist, the block matrix doesn't have an inverse. Yeah.
Go back to like where you found AX equals I from part 1 of that. Like what happened to the BZ?
We found Z was 0 in step 3.
Oh, right.
So because Z is equal to 0, when we go to number 1, the BZ term goes bye-bye. Special case, guys. What happens, so like, you know, sub-example of this example. I'll make a comment, by the way. If we had A, C, and we were inverting it, what would that be? See that? So in other words, I'll write the result over here. And this generalizes, by the way. Block diagonal matrix is invertible if and only if all its blocks are invertible. So the equation I'm suggesting with that sentence is this. If I have like A1, A2, da-da-da, say I've got K blocks, and I invert that. I can do that only if each one of the blocks is separately invertible. Yep.
This might be a silly question, but at the last step, or at the bottom step,
Mm-hmm.
down there, yeah. What's the algebra from getting AY equals negative BW to...
Oh, fair enough. So I multiply both sides by A inverse. So A inverse AY is equal to A inverse times minus BW. But that tells me that I times Y is equal to minus A inverse times BW. But that is minus A inverse B, and we've already found W was C inverse right here. So,
Thank you.
in the blue. Fair question. All right. So I think you guys, I've given you a question or two about block multiplication in your homework. Don't be scared of these. These are harmless. You just have to, you know, take them apart block by block. All right? But it's nothing you guys can't do. They just, you know, the point of the block multiplication is you have to, you know, kind of divide and conquer. Now, block multiplication is actually very important for industry and application, because basically what happens with, if you can find a block structure to a problem that you're looking at, an applied problem, what that means is that the arithmetic which is involved between the different blocks is kind of partitioned, right? Like you just look at involvement of data between the blocks, and it if you can find this kind of structure, it basically what's the word? It divides the data calculation into sub pieces, and like each piece only depends on the size of that piece. And since typical calculations involve like the square of the size of the matrix, it's a much smaller calculation. If you're talking about a 1,000 by 1,000 matrix, right, which you might be in an application, if you're talking about 1,000 squared, that's 1,000,000, right? But if you have little blocks that are like maybe 100 by 100, well, 100 squared is what? 10,000, right? So you might have 20 100 by 100 blocks or something, and that would be a much smaller calculation than like the full 1,000,000 by 1,000,000. So if we can divide the problem into a bunch of little problems, it becomes easier, numerically speaking. So block multiplication is important to know about. This is one of those things I did not learn in my undergraduate linear algebra. My first introduction to blocks was during my first test of graduate linear algebra. I was sitting there working on my test, and the professor comes over my shoulder. He looks down on my paper, because he'd do this about halfway through the test. He'd walk around and give people hints. I didn't realize that's what was happening, because he didn't tell us he was going to do this, but this is what was happening. And he just looks at my paper and he goes, "Use the blocks. Use the blocks." And I was like, "Thanks." But the thing is, I didn't know what a block was. But he was telling me I was making things needlessly complicated because I was insisting to calculate at the level of components rather than blocks. So anyway, it's something you should know about. It's not a big deal if you know about it. If you don't know about it, it can become a big deal if you learn about it on a test. All right. So I need to talk to you guys then. We're in transition topics here. I want to talk to you now about there's like really, I guess 2 big calculations, maybe 3. Fine, there's 3 big calculations we have left to learn this week, I think. And those calculations are how to find the basis for the column space, how to find the basis for the null space, and how to find and perhaps use the quote-unquote LU decomposition of a matrix. So pretty much all 3 of these are in one way or another partly answered by the column correspondence property. But in order to best appreciate the question of the null space basis, I think we'll start there. And I guess I should probably tell you what we mean by basis, right? Definition. What's a basis? A basis for some subspace of Rn is a set beta of vectors in Rn which so I guess I need to give the subspace a name. Let's call it W, which has, for one thing, beta is linearly independent, and the span of beta has to be equal to W. That's a basis. All right. So a basis is a linearly independent spanning set for a subspace. Now, you might be like, well, what's a subspace? Well, fine, 2 important subspaces that were really subspaces. One, an example of this would be the column space of A is a subspace. So let's say A is M by N. All right, so M by N matrix, how tall are the column vectors? N? What'd you say?
M is in
M as in mommy. Yes, I'm sorry. I'm an idiot. So this is a subspace actually of Rm. Right. So that less than or equal to is notation for subspace. All right. So if you were taking, Math 321, we'd spend a lot of time talking about how to prove things are subspaces. And here I'm just going to tell you, a subspace is simply a subset of Rn, which is closed under addition and scalar multiplication. It's like examples of subspace include lines through the origin, planes through the origin, and like volumes through the origin. All right, they're closed under multiplication and scalar addition. So column space is actually a subspace. And the other one is the so-called null space. And the null space, what it is x in Rn such that ax equals to 0. So we actually can prove that if you have 2 points in the null space, then the sum of those points is again in the null space. And a scalar multiple of that point is again in the null space. Right? This is true because if we talk about homogeneous solutions, if we add 2 homogeneous solutions together, we still have a homogeneous solution, right? So these are 2 important examples of subspaces. And we want to understand how to find the basis for either of these things. So let me, example 4 here, actually do that for a specific example. Suppose A is 1, 2, 3, I don't know, 2, 4, 6, 0, 1, 0, and finally 3, 6, 9. Oh, my bad. I meant to put a 7 in the middle. I'd like to show you how we can find the basis for the column space and the null space. All right? So, as I was saying, row reduction pretty much answers both of these. So I'll illustrate the method for you guys. All right, so let's get to it. We do row reduction. So we've got row 2 minus 2 row 1. And I'm going to do a 2 for row 3 minus 3 row 1. So that gives us a 0, a 0, a 1, 1, 0, 0, 0, 0. All right. Top row unchanged. Do we agree? All right. And then one more step and we'll be completely done with the row reduction here. We got what? We got row 1 minus 3 row 2. All right. I think, yep. Uh-oh, what'd I do? Oh, I was already done? Oh yeah, I just messed it up. Hey, well, thank you. I'm working too hard. I should have just stopped, right? Thank you. Muchas gracias. Sorry, I only know Sesame Street Spanish. I don't go as far as what you just said. Oh, you're welcome. Okay, well, I knew that. I was just being facetious. But actually, I haven't seen. Who knows what's on Sesame Street now? It's long since left my purview. But yeah, okay. Actually, after this one, multi-step row reduction here, you got to be careful with multi-step row reductions. They're not always legitimate. You can't mix like one of these and a row swap if the row you're modifying is involved in the swap. Be careful with that. But this is a legitimate move, and yes, that is the reduced echelon form of A. All right. So the column space of A, I guess I should give you the actual definition. The column space of A is the span of like column I, well, column J of A, such that, you know, J equals to 1, 2, however many columns there are. So for this, like in the abstract, it's n, but for us here, n equals to what? For this example, n equals to 4, right? So the question then is, what is a spanning set for the columns, right? Like which columns can I use to build any other columns? It's pretty obvious, right? The column correspondence property says that, hey, if we use these two, these are the pivot columns, right? I can obviously build columns 2 and columns 4 from those, right? And the column correspondence property says, hey, the same is true over here. For the most interesting one, perhaps, is that column 4, right? Column 4 of A is actually equals to what? It's actually equals to column 3 times column 1. 3 times column 1 of A plus what? 1 copy of column 3, right? Do you guys see that? I'm seeing that from looking at the 4th column here. I have 3 times the first pivot column plus 1 times the second pivot column. Column correspondence property tells me this. All right? And likewise, so the 4th column we can build from the 1st and the 3rd columns, right? And the 2nd column is just what? Twice the 1st column, right? So what's, we can put beta for the column space simply as 1, 2, 3 and 0, 1, 0, right? We can use pivot columns of A to form basis of column space of A, okay? And that's the general method. If you want to find the basis for the column space, row reduce, identify the pivot columns, they're your basis. They're automatically linearly independent because the pivot columns are nothing more in the reduced row echelon form of the matrix. They're nothing more than a subset of the standard basis, all right? And we know those are independent. All right, so great. So how about the null space? How do we figure that out? What's the null space of A? If X is in the null space of A, that means that X is equal to like X1, X2, X3, X4, right? It's 4-dimensional. And what can we see from these equations up here? We've got what? X1 is what? X1 is minus 2X2 minus 3X4. X2 is minus X4. My bad, X2 is what? I got to do better here. X2 is what? Oh, I'm sorry, I'm an idiot. X2 is X2, because X2 is what? X2 is a non-pivot column, so it just appears as a parameter. For X3, we have X3 is equal to X4, so I get like minus X4 here. And then finally, X4 is a parameter again. To try to make sure I don't lose you guys, do you guys understand what I did there? I skip one step, right? To write the solution for the from the reduced row echelon form, what is it there? Do you see it? The top row gives me what? What's the top row say? Exactly. So you told me x1 plus 2x2 plus 3x4 equals to 0, right? And the next one down, this says what? This says that x3 plus x4 is equal to 0. Now you say like, well, there's no 0, right? But remember, we can tack the 0 on, and it just rides along, right? So we can see solutions to the homogeneous problem without actually writing down the augmented coefficient matrix with the zeros in the last column, all right? It's a little bit of a trick, but it's not a big one. So this means x3 is minus x4, and x1 is minus 2x2 minus 3x4. This is always possible in the following sense. What I'm saying is always possible. You can always write the solution for x in the null space as a vector, a parameterized vector, where the parameters are the non-pivot variables. The non-pivot variables here are x2 and x4. Now once I do this, I can factor out x2. x2, I get a minus 2, a 1, a 0, and a 0. Plus x4 times minus 3, 0, minus 1, and 1. So what this shows me then is that the null space of A, actually it's the span of these two four-dimensional vectors, namely minus 2, 1, 0, 0, and minus 3, 0, minus 1, 1. So this is a basis for the null space here. And while I've just showed you for a particular example, this calculation is general. To calculate the basis for the null space, we simply look at the row reduction and we read the solution to the homogeneous equation and rewrite it as a span of particular vectors where the coefficients of the span are given by the non-pivotal variables. This always is possible. Now you might wonder, what does this mean, right? And something I don't always say in this course at this point is what it means. It's harder for me to say what the column space means. We can drag back to questions about spanning and so forth there. That's fine. But the null space, I think there's something interesting to say here. So you guys know the dot product, right? Okay, so if you look at these four-dimensional vectors, right, what do these have to do with the dot products of the matrix of A? Think about this. What is it? What's the deal? Minus 2, 1, 0, 0. If you go back and look at A, and you take the dot product of that vector with the row, like the first row, dot product, 0. Dot product of that row with the second row, 0. The dot product of minus 2, 1, 0, 0 with 3, 6, 0, 9, 0. Right? So if you think about this, the null space of A, it contains vectors which are perpendicular to the rows of A. So if you're like in 4 dimensions or something and you want to find out which directions are perpendicular to a given direction, we can use this calculation to figure that out. Which directions are perpendicular to these 3 directions? Those 2. And any linear combination of those 2 are perpendicular to these 3 directions, reading them as rows. So, yep.
Since there isn't a 4th row, how did you get x4?
Well, but it's a 3 by 4 matrix, so we have to multiply by 4 by 1. So this is like x1, x2, x3, x4. But I'm out of time. I got to stop here. So. Thanks, guys.